students, welcome back to another lecture of our course Environmental Modeling and Simulation. In today's lecture, we are going to use the concepts that we have learned throughout the course when it comes to geometric approach to solving our systems 1D and 2D to understand how we can go ahead and model outbreak of a disease. So this is one of the most preliminary epidemic model that has been used in our world, in our field of mathematics and public health. And we are going to look at how this model was developed, and it was proposed before the Bombay plague of 1906. And the scientists who proposed it, they saw that the model worked very well for the Bombay plague. We are briefly also going to discuss how this model can be improved or changed for other kinds of diseases. And if you remember from the tragic pandemic that we all went through recently, there were several models that were proposed at the beginning of the pandemic, SIR model, SIS model, and very briefly towards the end, I'm going to explain to you what those models are. However, I must say that the model we are going to study today is a very old, very simplified version of the models that are used now for predicting how diseases spread. However, they will still give you an idea of what R naught is, how diseases spread, how to model them, so that you can at least understand the conversation and then hopefully make your own better models. So let's get started. So remember, the first step of writing a model is to understand conceptually what's happening. So first we need to have a conceptual model of how this particular disease spreads. We're talking about a disease that is infectious and it spreads by direct contact between a healthy and susceptible person and an infected person. So it's not one of the diseases that spread through waterborne infections. It's not one of the diseases that spread through fomites or aerosols. We're talking about a disease that spreads through direct contact. So what we have are healthy people. These are healthy population and they are susceptible to the disease. That's another assumption we are making. Right here, you should understand, since susceptibility of healthy people to this disease is an assumption, if for some reason the population already has immunity to the disease, then there's a good chance that this model will absolutely fail. Alright, and then we have initial number of sick people. So we have some people who contract the disease somehow. This is our sick population. Now, every time the healthy and susceptible people interact with sick people, the nature of disease is that it will be transferred. And not every time. The success rate of transfer is not 100%, but it's something, it's a fixed ratio. That's the second assumption we are making. The second assumption, let me clarify, is that for n number of interactions between healthy and susceptible people and sick people, a fixed proportion of the healthy people will get sick. So let's say if healthy and sick people interact, as one sick person interacts with 10 healthy people, 4 of them fall sick. So that 4 number remains constant, whatever that number is. And this should already start ringing bells in your head that we are talking about, we are hinting towards the property of diseases, which we also call R naught. Okay, so every time there's an interaction between a healthy and susceptible person and a sick person, there's a fixed probability that the infection will spread. So we know that the number of healthy people over time will reduce. So what we are going to get is, let's say X is the number of healthy people in the population. And then Y is the number of sick people in the population at any given time. And then some percentage of sick people will not survive this disease. So let's call it fatalities. Some percentage of sick people do not survive this disease, which is a tragedy. That's what happens. Okay, so we know that the rate at which the healthy people will change over time in the population will depend upon the interaction between healthy and sick people. So we know that there's going to be a term here that shows product of healthy and sick people. Remember, if you're dealing with a non-dimensionalized system, product is the best way to go. Even when we are not dealing with non-dimensionalized system, if we want to show interaction between two entities, we have to multiply them. So some constant here, K, and a minus sign. Minus sign because the interaction between healthy and sick people is resulting in overall decline in the healthy population. On the other hand, for the sick people, we'll have every interaction between X and Y, between healthy and sick people, a fixed percentage of them are getting sick. So we have a plus sign here. So dx by dt is equal to minus kxy, dy by dt is equal to plus kxy. Now, if you go back to the population of healthy people, there are other factors happening. People are dying because of other diseases, old age, and people are also getting born. Now, this is where we make our next assumption. The next assumption that we are making in this epidemic model, very simple Kermack epidemic model, is that the disease is spreading so fast that we can ignore the changes in the value of X due to usual things like birth and death due to other causes. Death will reduce the number of healthy people, so we need to subtract minus death due to other causes. Now, obviously, since we are talking about the fatalities in this epidemic, we need to talk about how the rate of dead people is changing. Number of people who are dying, how is that changing? Now, we know that a fixed proportion, again, this is an assumption we are making, a fixed proportion of the people who fall sick will not survive the disease. Now, this is an assumption because that's not always true. The science of medicine is always improving, always developing, learning new things. So we're always coming up with better treatment techniques, better medicines, and technologies to help people survive infectious diseases. But here we are saying for the time scale of the outbreak, the infection is spreading so fast that medical technologies are not able to catch up, or we have already sort of reached the limit of medical technology that we can get in such a short time, and a fixed proportion of sick people will probably not make it. This is known as fatality ratio. What proportion of sick people do not survive? So dz by dt clearly will be proportional to number of sick people. So no interaction is happening. Sick people don't have to interact with healthy people or other sick people to affect their fatality rate. It's just directly proportional to YL. Now, since sick people are dying at this fixed rate, number of sick people will also reduce. So we need another term here, minus Ly. This is your very basic model. Now, I need to make one correction to this model. Since we said that birth and death due to other causes or natural birth process, we can consider this 0 for this time scale because the disease is spreading fast enough that we can ignore the death due to other causes, natural causes, and other diseases, the usual birth rate. So now the question arises, are we dealing with a 3D system because we have 3 variables, X, Y, and Z or Z that are changing with time? Now it looks like a 3D system, and there's a very simple way to convert this particular system into 1D system, and that's the first way in which we are going to approach. Once we finish this, once we learn how to modify this very simple model to fit other diseases, the way other diseases spread, once I tell you about how to incorporate SIS, SIR, then we look at the second approach to solve this epidemic model, one that uses what you learned in 2D systems, the Null-Klein method. Okay, so what I'm going to do here is I'm going to convert this 3-dimensional model into a 1-dimensional model, make it very easy. Now look at the third equation here, dz by dt is equal to Ly. Now what I can do is I can take the y and I can substitute here in the first equation. So what I'll get is dx by dt is equal to minus kx 1 by L dz by dt. Now this is a very simple 1-dimensional system where the variables can be separated, right? So all the z's can come, z's or z's, I'm going to stick with z. All the z's can come in one place and all the x can come in one place, one side of the equal sign. So we have dx by x dt is equal to minus 1k by L dz by dt. Now we can integrate these separately and we'll get log x. From x naught to x, we are not using integration constant because we know where we are starting from. We are going from x naught to x. X naught is the initial number of healthy people in the population. X is the current, xt, the current number of healthy people in the population. And zt is the number of dead people. Now this is, this sounds like a very trivial way of approaching this problem. We are not even using geometric approach right now. Now here's the thing. It seems very trivial, but it's very important. When an epidemic spreads, especially in a country where we do not have a very strong, well connected, well documented healthcare system, we will not be able to keep a track of the exact number of sick people. Maybe because of issues with our ability to test people, the number of people who are coming to hospitals to get tested, or the number of people who are using traditional medicines and other ways of healing, other approaches to healing, or people who can't even afford coming and getting the healthcare. Or in case the healthcare infrastructure gets overburdened, they will not be able to keep an account of how many people truly fell sick. So why is very hard to count in situations in low and middle income countries such as our own. So as the disease spreads, so let's say the disease is spreading, you are a public health official, you want to keep track of the number of healthy people with time, how that is changing. You want to keep a track of sick people with time, how that is changing, hopefully going down. And then you want to keep a track of how the casualties due to the disease are changing. Number of healthy people is very hard to track. Number of sick people in low and middle income countries with limited healthcare infrastructure is also very hard to track. But it is typically much more reliable to count the number of people who die during an epidemic, the number of excess death. So what we'll be reporting here would be death due to other causes, plus death due to outbreak of the disease. So this is known as the excess death because the death record keeping is typically good across the globe. Typically, it's much more reliable to look at the number of casualties. So at any given time, we may not know what is the XT, we may not know what is the YT, but we may have a better idea of what the ZT is, which is the deaths that can be attributed to spread of the disease. So if we know how Z is changing with time, we can use this very simplified one-dimensional model that looks at the rate of healthy people changing with and correlates it with number of dead people at a given time, and we can understand how many healthy people still remain. So let's write this equation. We have x is equal to x naught e to the power minus kl zt. So this is an integration. Now you may be wondering, where's the geometric approach here? Why did we learn geometric approach if we were to integrate? This is easy part, so we're using analytical approach. In fact, this is just step 1. We're going to go in step 2. Look at the number of sick people at any given time. Because see, to understand how the disease is spreading, the death count is more informative. We can see how the number of healthy people is changing with time. But to marshal our resources, our healthcare resources, to understand how much our health budget should be, to understand where which province, which area needs what kind of health supplies, we need to know the number of sick people. So, okay, we know the rate at which healthy people are falling sick. We know the excess death and how it is changing with time. We also need to find out the rate at which people are falling sick. So, we are going to use this information here to find this out. How? Let's look at next slide. Okay, so let me rewrite the equations once. We have dx by dt, rate at which healthy population is changing, minus kxy, rate at which sick population is changing, plus kxy. So the healthy people are moving here, minus ly, the rate at which the death count is increasing is ly. There's a simpler way of writing this, like which helps people understand what's happening. You can make 3 boxes: healthy, infected, the ones who have passed away. So let's say one box is healthy population, then we have infected population, and then we have people who passed away, the death count. So the rate at which healthy people are turning into infected people, so it's like a chemical reaction, is minus ki. In this case, I'm using I because here I is infected people. So I know that this is the rate constant for H to turn into I. So right away I know the flow from H to I is equal to minus Ki into H. Now I are turning into D and it is proportional to L. So I know the rate at which infected people are changing. So just by looking at this diagram, I right away know I can write an equation for di by dt, which is I is increasing, when the movement is happening from h to I. So plus ki into h. Actually, I should remove the minus sign from here because the direction is enough. If you look at the direction of the direction of flow is h to I. So when I'm looking at the flow from h to I, it's plus ki. When I'm looking at flow from I to h, it's minus ki. And then from I to d, so the flow is I to d, right? So if I'm looking at I is losing the number, so minus Li. Now if I want to use this diagram to write dH by dt, again very easy. H is losing number from h to I, so it is minus KIH, and then dd by dt is also pretty easy. D is increasing Li. So yeah, a graphical way of writing the model. It is used, you will come across this in many papers. And when we study the global warming potential, the global emission, the GHG emissions, greenhouse gas emission, and its relationship with the GDP growth rate, we will use a diagram like this to first conceptually write the model, then write the mathematical model, and then go ahead and solve it. Okay. So remember, we want to find out why, how y is changing with time. So what I'm going to do is just look at this model. Things are pretty easy. If I add up the three equations, what do I get? If I add up dx by dt, dy by dt, and dz by dt, dz by dt, what I'm getting is 0, which tells me that at any given instant, total x, y, plus z is equal to constant. Now here is a big assumption. I'm assuming death due to other causes is not accounted in this, or the epidemic or the outbreak is happening fast enough for it to be ignored. And also the birth process is ignored here. So let's say this constant is n. Okay, that's what's going to make our life easy. So we know x plus y plus z is equal to n. We know the equation for x. We found out that equation in the last slide. Okay, so this is x. And then we have y, and then we have z, which is zt is equal to n. So we have x, y, and z equal to n. Look at here, look at this, we have two variables only in the system, y and z. So we are going to express y as a count of z. So yt is equal to n minus zt minus x naught e by L. So now we have expressed the number of sick people at any given time in terms of Z. Okay, now one thing I want you to notice that we have expressed the number of sick people in the population in terms of death. In the previous slide, I talked about how death count is the easiest count for low and middle income countries with compromised healthcare infrastructure to maintain. So again, by using the information that we are getting from death count, we can predict, we can estimate the number of sick people at any given time. However, this equation is an absolute equation. It does not tell us how y is changing with time. So what we are going to do is we are going to use this information and we are going to find out how we can get a dynamic equation from the integration that we have done and from the substitution that we have done. Okay. So y is here. Now let us put this information in the third equation, and now we get dz by dt, rate at which the death count is changing, because remember, death count is the easiest count to have in case of an outbreak in a country like ours. So we also need to know, is the epidemic ending? Are we going to expect more casualties, less casualties? So for that, we need to figure out how dz by dt is changing. What is dz by dt? So we can take the y information that we have here, that we just got, and substitute it in the third equation here. That's what we are going to do. So we get L into n minus zt minus x naught e minus k by L zt. So now we have one variable, one system. We have reduced a three-dimensional system into a one-dimensional system. This is okay right now for the purpose that we are doing. This is not always okay. When we are able to reduce a 3D system into a 1D system or a 2D system for ease of calculations, for ease of understanding, we do lose some information, because after all, the system is a 3D system. Okay, but now we have 1D system for the rate at which the death count is changing over time. Now this system we can analyze by drawing face portrait. We can understand, is the death going to increase, is the death going to decrease, and then remember the death count will help us understand how the number of sick people is changing, how number of healthy people are changing. That we have already done. Now this seems like a very complicated system here. We have some really interesting multiplication between two numbers. We have z here, and then we have this constant minus k by L multiplied to zt, which is a power. We need to non-dimensionalize this system. So let's go ahead with that. Now for non-dimensionalizing the system, I'm going to use a trick. The trick is, wherever you know that something is supposed to be non-dimensional, first make that non-dimensional. For example, e to the power something, we know that this cannot be a dimension. It has to be a non-dimensional power if you are putting it e to the power something. So I'm going to check the dimensions of minus k by L zt, which is the exponent of e. So look at k, the unit of k. Let's look at the first equation. On the left side, dx by dt, so we have number by time. On right hand side, we have k, and then we have number and another number. So we know that the unit of k should be, for LHS to equal RHS, should be 1 upon time into number. So unit of k is 1 upon time into number. Zt is number. And now let's look at the unit of L. For L, we go to the third equation. We can also use the second equation, doesn't matter. On left side, we have number by time. Z is a number, t is time. On right side, we have a number. And then L unit has to be per time for LHS unit to equal RHS unit. So we know that the unit of L is 1 by time. So we put 1 by time here, and you see all these units will cancel each other, and we are left with a non-dimensional power, non-dimensional exponent for E. So what we can do is we can define a new variable, a non-dimensional variable, let's call it U. So U is equal to minus kz by L. Okay. So if U is equal to minus kz by L, so we can substitute it here, becomes very simple, x naught e to the power minus u. So kz by L zt, zt is equal to u. So zt is equal to Lu by k. We can substitute this here, and we'll get and then we can differentiate this, so we get dz is equal to, so we can substitute this on the left hand side. Okay, so this is our equation. I'll erase this part to make more space. So now what we have basically is, we can cancel the L's on both sides. So we have du by k dt is equal to n minus L u by k minus x naught e minus u. So if you look at the unit here, what unit we are dealing with? Both LHS and RHS have the unit of number. So we need to get rid of number. So let's do one thing. Since I'm going to make a face portrait, I want to make my life easier. And I know that here I'm going to, once I non-dimensionalize, this is going to be a very easy line to draw. This, however, is going to be a curve. So if the curve has a coefficient, e minus u has a coefficient attached to it. If I'm trying to understand how things change when I change the parameter, when I change the coefficient, this is going to be more difficult to draw. So what I'm going to do is I'm going to divide LHS and RHS by x naught. So let's take x naught and divide the whole system by x naught. So we get du by k x naught dt there we go. So now I need to define new time, and because t is still dimensional, and I need to define new variables that are non-dimensional. So one very easy way is that we can define the new time so that this thing becomes equal to tau. So we can say kx naught dt is equal to d tau, which means tau was equal to kx naught t. So let's substitute that. And I'm going to write here, sorry for the hodgepodge, we are going to get du by d tau is equal to n by x naught minus L k x naught u minus e to the power minus u. So this is the system we have arrived at. Let's write it on the next slide. Du by d tau is equal to okay, we have a line, this is our line, and this is our curve. So phase portrait is going to be very easy, relatively easy. Now let's look at the things that we have defined. We have defined u is equal to minus k by L zt. We have defined tau as kx naught t. And now we have two sets of parameters, n by x naught and L by kx naught, which are still having dimensions, but overall as a product they are dimensionless. So now we can define A is equal to n by x naught and B is equal to L kx naught. So now our system has been completely non-dimensionalized. Du by d tau is equal to A minus Bu minus E minus U. I hope you can see the line and the curve more clearly now. Now, before we go ahead and draw phase portrait for this 1D system, let's look at the substitutions we have made. We have A is equal to n by x naught. This is a very important substitution. A equal to n by x naught. What does n by x naught tell me? N by x naught tells me total people, total population divided by initial number of healthy people. So let's say the total population is 1000 units. The initial number of healthy people are 999. So there's only 1 unit sick people. Then A would have certain value. Now let's look at another scenario. 1000 people, but the initial number of sick people are 100. So now the A looks very different. So the A changes according to the initial number of sick people, and we can already see that it's going to have some impact. And if you remember the similar kind of equations that we have drawn phase portrait of, A minus Bu is definitely going to have impact. The other thing I want you to notice is that since initial number of healthy people can never be more than total population, A is always going to be greater than 1. This is very important because if you look at our curve in the first quadrant where U and time are positive because time can't be negative, so we are not going to go in second and third quadrant, and we want U to be positive because natural numbers cannot be negative. We are dealing with number of people, can't be negative. So in the first quadrant, the highest value that this curve can have is 1. So A is always going to be more than 1, and A is the intercept of your line. So again, A is a very important number. Now let's look at B. What is B telling us? B is telling us about L, which is the fatality rate. What ratio of sick people are going to die, divided by K, the rate at which people are going to fall sick, and the healthy people. So this is basically giving me some idea, not exactly, but some idea of the rate at which people are going to die. And this is telling me some idea about the infection rate, initial infection rate. So B is the ratio of that. This is also very important and we'll very soon come to it. In the next lecture, we are going to draw a phase portrait. We are going to understand why taking a moment to discuss A and B was important. We are going to also look at how this very simple model can tell us whether this new infection is going to blow up into an epidemic or it's going to be contained like a minor outbreak. That's all for today. See you in the next lecture. Thank you.